Welcome to lecture number 7 of chapter 4 series. Now in this video we are going to discuss integrated rate equation for first order reaction when reaction is in gas phase. Yesterday we learned about first order reaction, but that was in case of liquid and solid phase. Now here the reaction is in gaseous phase. So instead of concentration we are using partial pressure here. Pressure term we are going to use here. So first of all, take a reaction. A gives B plus C here. All the components are in gaseous phase, reactant as well as product. So at initial stage, the total pressure is Pi at initial stage. At initial stage, the partial pressure of component A, the pressure of component A only, that is partial pressure of component A, that is Pa. Similarly for component B, the partial pressure is Pb, and for component C, the partial pressure is Pc. Now by Dalton's law we can say that Pi is equal to Pa plus Pb plus Pc. Total pressure is equal to sum of partial pressure. That was the Dalton's law. Now I am writing down again the reaction here. A gives B plus C. At initial stage, suppose at time t is equal to 0, at starting point, product will be 0 here because reaction is not yet started. So product is 0 here and total pressure is Pi. It is pressure of component A only because B and C are 0 here. So pressure of component A is Pi. Now at time t is equal to t, the pressure becomes Pi minus x. Minus x, why? Because x amount of pressure that converted into product. So pressure of B is x and pressure of C is x here. Pressure of reaction, that is Pi minus x. Now suppose at time t is equal to t, the total pressure is Pt. Now by Dalton's law, again here I am applying the Dalton's law. Pt is equal to total of these three terms, total pressure Pi minus x plus x plus x. So here I have written that Pi minus x plus x plus x. Minus x plus x will be cancelled out. So I will get Pt is equal to Pi plus x. So I can derive x is equal to Pt minus Pi. Now at time t is equal to t, partial pressure of component A is Pa. Suppose partial pressure of component A is Pa. So here I have written Pa is equal to Pi minus x. Here it is written Pi minus x. So here that only I have written. Instead of x I can write this. So instead of x I am writing Pt minus Pi. So Pi minus Pt minus Pi. Minus minus will be positive here. So 2Pi minus Pt. That is our equation number 2. Pa is equal to 2Pi minus Pt. Now this equation we derived it yesterday. K is equal to minus 1 by T into 2.303 into log into concentration of reactant divided by concentration of reactant at initial stage R0. Now instead of concentration I am using pressure here. So instead of R I am writing Ca here, pressure at time t, and instead of R0 I am writing Pi, initial total pressure. So Pi I am writing here. Rest of them it is same, minus 1 by T 2.303 log Pa divided by Pi. Now if I want to remove this minus sign, I have to interchange the numerator and denominator. So I am writing Pi divided by Pa here. Now this Pa value we derived here, equation number 2 in that Pa is equal to 2Pi minus Pt was there. So instead of Pa, I am writing 2Pi minus Pt here. Rest of this is same. 1 by T 2.303 log Pi divided by 2Pi minus Pt. That is our equation to derive K when our reaction is first order reaction and it is in gaseous phase. Now the next topic is half-life of reaction. Now what is half-life of reaction? So suppose we have 100 molecule of reactant. Now it reacts with some another reactant and it becomes 50%, means 50 atoms will be remaining in the reaction as reactant and 50 atoms will be converted into proton. So this time duration is called half-life. So here definition is written: time at which concentration of reactant reduced to half of its initial concentration. That time is called half-life of reaction. Again, time at which concentration of reactant becomes half of its initial concentration. That time is called half-life of reaction. Now here we are going to derive equation for half-life for zero order and first order reaction. First, for zero order reaction, this is the integrated rate equation that we derived. R is equal to minus Kt plus R0. Integrated rate equation. Now I am just rearranging that equation. R minus R0 is equal to minus Kt here. Now I want to derive K here, so I am rearranging this formula also. So R0 minus R, because minus sign is removed here, so I am writing R0 minus R divided by T here. T was in multiplying here, now it is in division. So R0 minus R divided by T is equal to K. Now suppose at time T is equal to T1 half, the concentration becomes half of its initial. So R is equal to R0 by 2. R0, that is initial concentration, and it is reduced to half. So R0 by 2. So I am putting these two values in this equation. So K is equal to R0 as such, initial concentration. Instead of R, at time T is equal to T1 half, instead of R, I am writing R0 by 2. So R0 by 2, and instead of T I am writing T1 half here. So now change the side of T1 half and K. T1 half is equal to R0 minus R0 by 2 divided by K. Now take LCM here. So 2R0 minus R0 divided by 2 into K. Now 2R0 minus R0 means 1 R0 will be there. So R0 divided by 2K. This is our equation for half-life for zero order reaction. Now for first order reaction, same method we will follow here. First, write down the integrated rate equation. For first order reaction, that equation was ln R is equal to minus Kt plus ln R0. R0, that is initial concentration of reactant. R, that is concentration of reactant at time T. Now I am changing the sign of ln R0. So ln R minus ln R0 is equal to minus Kt. Now minus sign is there between two logarithms, so two values will be in division. So ln R divided by R0 is equal to minus Kt. Now if I want to remove this minus sign, I have to change the numerator and denominator here. So I am writing ln R0 divided by R is equal to Kt. So T is equal to 1 by K into ln R0 divided by R. Now suppose at time T 1 half, the concentration becomes half of its initial. So R is equal to R0 by 2. Concentration becomes half of its initial. Initial was R0 and half half of that is R0 by 2. So instead of T, I am writing T1 half here. T1 half is equal to 1 by K into ln R0. Instead of R, I am adding R0 by 2. Now R0 will be cancelled out, and these 2 will be in numerator because it is denominator of denominator. So it will be in numerator. So 1 by K into ln 2. Now convert this ln into log. So I will get T1 half is equal to 1 by K into 2.303 into log 2. Log 2 value is 0.301. So I have written this here 1 by K into 2.303 into 0.301. Now if you multiply these two, you will get 0.693 divided by K. So T1 half for first order reaction is equal to 0.693 divided by K. This is the half-life equation for first order reaction. Now in this equation, you can see that half-life of first order reaction, that is independent of concentration. Here concentration term is not there. So half-life of first order reaction, it is independent of concentration. It is only based on rate constant K. It only depends on rate constant K. It is independent of concentration here. Now, next topic is pseudo first order reaction. Now, what is pseudo first order reaction? Means the reaction is not originally first order reaction. The order is different here, but due to some condition, it seems like it is first order reaction. It is not originally first order reaction, but due to some condition, it seems like first order reaction. Take an example here. Suppose I have ester here. Ester compound reacts with H2O and forms acid plus alcohol. Now here you can see at time T is equal to 0, the concentration of ester, that is 0.01 mole, and concentration of water is 10 mole. You can see the difference here. Water is in large excess amount and ester compound is very less here. At initial stage, at the beginning, the product is 0 here. Now suppose at time T is equal to T, the ester compound is used completely. So it becomes 0 mole here. And water becomes 9.9 mole. This much moles of from 10 moles will be used here. So it will be 9.9 mole. And acid and alcohol, that will be 0.1 mole almost. Now here you can see these two are having very less gap. 10 and 9.9 is almost 10. So concentration of water that remains constant here throughout the reaction. So when one reactant is in large excess amount, its concentration is taken as constant. So rate is equal to K into concentration of ester. Here originally water will be there. If concentration is low, water will be there. But here concentration of water is very high. So I am not writing H2O here. It is taken as constant. It does not change with time. So only ester is written here. Concentration of ester is written here. And it is having power 1. So it is first order reaction. Why it is like that? Because water is in large excess amount. This condition is that if water is in less amount, then water concentration will be here.